Hello, everyone. My name is Arthur Olshire, and I'm a student at the University of Toronto, currently working as an intern at NVIDIA. And today I'll be presenting our work on Sim-to-Remote Real, a system for training dexterous in-hand manipulation with desktop-scale compute and transferring to a remote robot. Hopefully, you'll find some of the information in this presentation useful when you're creating similar systems and doing Sim-to-Real with Isaac Gym infrastructure. So the task that we've worked on in this work originated in last year's Real Robot Challenge. The Max Planck Institute for Intelligent Systems provided access to remote Trifinger robots, which were designed to be an open and low-cost alternative to other systems such as the Shadow or Allegro hand. Researchers from around the world were invited to submit code and run it on the robots. The goal of the task is to learn to repose a cube in 6 degrees of freedom using the Trifinger robot. Learning is to be done entirely in simulation and transferred to a real system. Policy inference in real life is done remotely, and there was no physical access to the robot during the development of the algorithm. We have access to noisy cube pose information from camera tracking. Previous work has shown the ability of reinforcement learning algorithms to learn complex manipulation behavior in simulators. This work is impressive, but the applicability has been limited by the thousands of worker CPUs required to train and tune the system, and dependent on expensive hardware such as the Shadow hand. The results of the Real Robot Challenge bore this out. Leveraging the research in model-free RL in new manipulation problems is challenging, and what happened was successful teams basically used hand-tuned policies specifically designed for this task. And this is largely due to the slowness in training using CPU-based simulators, where people had to train for days to learn anything on the Trifinger platform, even on simple reaching tasks. On the other hand, as Victor and Gav have talked about previously, the use of GPU acceleration with Isaac Gym has shown the promise to hugely reduce the computational requirements for training manipulation policies. However, these policies have still relied on Shadow hand, which is a very expensive hardware setup, limited to controlling orientation only, and haven't yet shown Sim-to-Real. So the motivation for the Trifinger project is thus several-fold. Firstly, we present an accessible framework for learning in-hand manipulation and show that it can transfer to a real system using far fewer computational resources than previous works, as well as low-cost robot hardware. Secondly, we show that we can repose in 6 degrees of freedom, both position and translation, with a single learned manipulation policy, and that this is enabled by key point representations. Further, we show that our policy can be transferred to a remote robot. And finally, we showed that we open source our work to allow other researchers to reproduce our results. And our hope is that this can serve as an example for how others can implement similar approaches to Sim-to-Real with Isaac Gym. Environment creation was simple. Using the URDFs provided by the Trifinger organizers, we could import them to Isaac Gym with no modifications. Isaac Gym requires convex collision meshes, so we enable the built-in convex decomposition for the Trifinger model and stage. The robot and arena are both imported as fixed, while the cube is allowed to be a free, rigid body. There is also the question of what action space to use, position, velocity, or torque on the joints. We opted to use torque following previous work in the space of in-hand manipulation and to demonstrate the fidelity of physics modeling in Isaac Gym. Thus, our action space became 9 degrees of freedom representing the joints of the robot. Our system works using a third-party reinforcement learning library with a PPO implementation. It was straightforward to integrate Isaac Gym with this framework due to the standard PyTorch format of environment tensors. We modified the front end of Isaac Gym to allow for easy configuration of experiments using Hydra. This was very helpful for tuning aspects such as hyperparameters and trying out different reward functions. Finally, we added environment logic to support different difficulty levels of goals and randomize the goal position to be able to learn all possible 6 degree of freedom poses. Again, this was simple to do using PyTorch and the provided Isaac Gym tensor APIs. Training setup is as follows. We uniformly sample 6 degree of freedom poses within the arena. Within each episode, the goal pose is fixed. This is because, unlike previous works, a big part of the challenge of the Trifinger task in particular is holding the cube in place. In fact, our success metric is also stricter since we only count successes as holding the cube within an epsilon threshold of the target pose at the end of each fixed length episode. So there are several challenges that we have when transferring a policy learned in simulation to a real robot. Even if you have a really good CAD model, there's always unknown physics parameters when doing such transfer. These can include friction, which is hard to model accurately even in high fidelity simulators. The masses of various objects or even the scale of the object can be unknown. Furthermore, there are limitations on the sensors that we have in the real world. Some states available in the simulator are difficult to observe in real life, and even measurements which we do have are inherently noisy. This is why Sim2Real is such a good test of the fidelity of a simulation system and the robustness of algorithms trained within it. Minimizing the size of the gap between the conditions in the simulator and those in real life is critical. So yeah, just recapping some of what Victor has talked about earlier. So domain randomization is a technique where we sample a wide range of simulation parameters from a distribution. This means that policies learned in simulation must be robust to a range of dynamics models. And this ideally means that they transfer better to the real world as the true values of the parameters are within the distribution of noise that the policy has been trained on in the simulator. In the Trifinger project, we leveraged Isaac Jim's domain randomization APIs to randomize these simulator dynamics. There are three ways in which we performed randomization. Firstly, by scaling the dynamics parameters of the environment. For these, we picked a reasonable default value and randomly scaled it up and down from a scaling distribution with unit mean. We applied these randomizations for the friction of the cube and ground, the mass of the cube, and the size of the cube. We also performed another kind of randomization to simulate noise from the sensors and effectors on the robot. This took the form of random delays on the cube pose observations to simulate camera behavior. We also added zero mean random noise to both the observations of the policy and the actions taken. Finally, to generate more robust grasps, we apply random forces on the cube to ensure that the robot gets a stable grip on it. For observations, actions, and random forces, we applied noise on both a per time step as well as on a per episode basis. And this is to ensure that the policies learned are robust to both stochastic delays and modeling mismatches. And another well-known trick that we can use to get good training performance, which is also able to be implemented in Isaac Jim, is asymmetric observations. So RL algorithms such as PPO have both a policy and a value function, but only the policy is run on the real robot. So we can use this to improve training by giving the value function extra information that's only available in the simulator and not in reality. The information available to us in the Trifinger task during inference on the robot was joint position, joint velocity, and object pose. Whereas in the simulator, we also had access to joint torques, fingertip positions, fingertip forces, and the velocity of the cube. In our experiments with Trifinger, this technique dramatically improved the performance during training. To recap, our pipeline starts with training via reinforcement learning. We used a highly optimized version of the PPO algorithm with an asymmetric actor and critic. Our policy architecture is shown. The actor gets the pose of the cube plus noise designed to simulate that of the camera, along with the joint states of the robot with noise. The output of the policy is joint torques plus noise. Our policy is trained using the Isaac Jim simulator, which is tailored towards high-performance GPU-based robotic simulation. And following previous work on in-hand manipulation, we introduce environment randomizations on friction, object mass, and object scale to improve the robustness of learned policies. Using GPU-based simulation allows us to train on a single desktop-level GPU, in contrast to previous works. And following previous works, the initial reward function that we used to encourage the cube to move towards the goal was basically formulated like this: the sum of kernels on the angular difference between the target and goal rotations, and the L2 norm between the current and target cube position. And our first experiment was to see how well such a reward fared for a 6 degree of freedom orientation and translation task in tandem with the large-scale training provided by Isaac Jim. And despite trying many different kernels and relative weights for a reward of this format, we weren't able to achieve good performance with this system. And video rollouts bear this out, showing difficulty in learning to reorient the cube. What's happening becomes apparent when we look at the success rate measured at the end of each episode for position and orientation. This is defined by being within an epsilon threshold of the goal position and goal orientation at the end of each fixed length episode. While position success increases quickly, even after 1 billion time steps, the orientation reward is only achieved 40% of the time. This demonstrates the difficulty of balancing the position and orientation components of reward when using this common formulation. Since using position and quaternion directly in the observation reward functions for RL led to poor policy performance, we searched for alternative representations of pose. We tried using 8 key points in 3D space sampled at the cube vertices for both the current and goal poses. These are easy to generate given the cube's Cartesian position and orientation using PyTorch and the Isaac-Gym tensor API. The representation could be used in extensions to other objects, which is not the primary focus of our work. We used key points to reformulate the reward into a sum of L2 difference between the current and target key point positions, plus a nonlinear kernel, which converts an L2 distance into a bounded reward. Our original policy observations were position and quaternion of the current and target pose concatenated. With key points, we tried changing this to use the current and goal pose key points concatenated together as policy input. And so we investigated the impact that the change in representation of pose had during training. And despite the simplicity of the change in representation, it produces a huge improvement in training performance. The average success rate of 5 seeds is about 85% with key points in the observation and reward, and under 60% without either. These results show the numerical benefit of a change in representation for computation of the reward and observation. The net result of these techniques is a policy which is able to learn the task well in simulation. It gives good performance on the 6 degree of freedom reposing task, even with randomizations applied. We also ended up with various emergent behaviors in simulation. So for example, the robot will sometimes rotate the cube in hand, but where this is not possible due to the fact that it only has 3 fingers, it will actually drop the cube on purpose and re-grasp it. And that shows the ability to learn longer term behavior when you've got a lot of data, even at the cost of short-term reward. And as mentioned previously, we performed sim to real remotely on the robot provided by the organizers of the Real Robot Challenge. After training, the first step in the process is uploading the weights of the trained policy to the remote computer. Then rollouts of the reposing task are performed on the real robot. The cube is tracked using 3 cameras, and we translate the position and quaternion output by the system to key points before passing them to the policy. And we also get proprioceptive information from the robot's encoders. As a result of the various randomizations applied, our policies are able to transfer well to the real Trifinger robot. We achieve an 83% success rate in deployment, defined as having the cube held in the target position at a predefined instant in time. Shown here is a representative sample of 5 successes and 1 failure to achieve the goal. Thus, despite the slower iteration cycles involved with using a remote robot, we're able to achieve good performance on a real robot with a policy trained entirely in Isaac-Gym. We can see in these rollouts the techniques which are learned to overcome the challenges inherent to the Trifinger morphology, and yet still get good performance on reposing in 6 degrees of freedom. For example, we see how the robot has to learn to drop and re-grasp to achieve some challenging orientations, which is, as I mentioned, surprising given that it has to trade off short-term reward for longer-term behavior. And so we wanted to push the limits of generalization of our policies to see how well it transferred to other objects or other scales without retraining. And so first we tried with different scales of the cube. And surprisingly, despite the initial scaling range that we used for domain randomization and simulation only being plus or minus 3%, our policies transferred to a very large scale range, up to 40% smaller and 20% bigger than the original cube. So you can see the these two different scales on the right. And what was even more interesting was that qualitative rollouts on objects with different shapes showed surprising robustness to object morphology, even though the original policy was only trained on a cube. So for example, we're able to repose a ball with key points like still sampled in the same places as they are for a cube, as well as a cuboid, which is only 1/3 of the size of the original object along one of the axes. This was quite surprising given that it really was only trained on one object. So we didn't really expect that, but it seems to be learning some kind of heuristics rather than just very rigid policies. And so finally, I'd like to acknowledge that the many people this would have been impossible without. Firstly, the organizers of the Real Robot Challenge, who provided access to the robots, as well as the amazing infrastructure that basically just allows you to upload your code and run it on like thousands of kilometers away. And also my collaborators at NVIDIA and the University of Toronto, who are shown on screen, including Mayank, Varun, Dennis, Victor, Ankur, and Animesh. So thank you everyone for listening. Yeah, and I guess I'll take any questions now if people have them.
You may want to also mention the time it takes to train.
Oh yeah. So for us, it takes about, we ran over our experiments for around around 24 hours. So if I go back to this graph here, so you can see like this is the reward curve. 24 hours is on the right. But it basically hits like the eventual like convergence reward at around, let's say 6 hours or something. It probably is possible to optimize this further, but already key points were a huge jump for us because, as you can see, like based on the success rate, for like this was our, at the bottom, the green curve was our original attempt, and that just took forever to train. So yeah, there definitely is more performance to be squeezed out of this. And Krishnan asked, do you see any finger gating in the learned policy, or does it typically try to put the cube back down to regrasp? So it generally only puts the cube down to regrasp when it would be really impossible. So if you actually try and use 3 fingers to orient something with your hand upside down, it's really hard, especially if like the object is a comparable size to the fingers. And so there's certain situations where it's really, really difficult to actually rotate it to a certain position. For example, if I'm trying to rotate it like that and I have to go beyond a certain angle. And so in those situations, it generally drops it. But there's a lot of times when, yeah, it does like this, either like finger gating behavior where it will slide the fingers along the cube, or it will like can pivot it like in the hand and things like that. So yeah. What are our plans for future work? We're still kind of debating that, but ideally we'd want to extend it more towards like a vision approach, because right now we're only doing things from states. And so doing sim to real on, yeah, with vision or with other objects, trading on more objects, those kinds of directions are very interesting to us.
You may want to mention that the cube pose is given to you by the organizers, etc.
Yeah. I think I did mention that in the talk, but yeah, that right now their system has like a camera tracking, which does like an optimization to get the pose of the cube. So we're not doing that vision system directly. And also like currently it would be quite difficult for us to implement that because the computer that this is running on is just a CPU, like the inference computer that they have for the challenge. So obviously optimization-based approach will work much better on that than doing something like a neural net. But obviously you would probably want something more complex like a ConvNet or something to actually extend to other objects or a wider variety of situations.
On that question, one of the things that we have with Omniverse and some of the tooling that we have in Isaac Sim and elsewhere in Omniverse, we have a quite extensive synthetic data infrastructure that exists in there, and we're using that to play around with this kind of vision-based training, and that's very similar to other things that we're doing with that Omniverse synthetic data infrastructure for areas such as our autonomous vehicle simulators.
Yeah. So we're definitely very interested in the vision angle. And then Krishnan also asked, do we add any observation noise in the simulator to train the policy? So yeah, we do. I talked about this briefly in the domain randomization bit, but we found that like the observation and the observation noise in particular was super important for, we don't have like scientific like what's the success rate with and without domain randomization. We do want to like do that eventually and publish it, but yeah, we don't have that right now. But anecdotally, when I added domain randomization, it massively improved the sim to real transfer performance. So yeah, and I think the randomization stuff that we did, such as random forces, observation, and action noise, were what allowed the policy to be robust enough to transfer to like these unseen objects, as well as different scales and things like that. So yeah.
Maybe I can just quickly ask, given the spectacular effect that the encoding of the reward had, did you try also the same kind of key point trick with maybe other environments that are hard to train? I guess for deformable objects, this would be hard, for a lot of rigid objects, right? This could be something useful.
Yes,
although...
yeah. So I think that that Anko and Victor are working with some other people who've been trying it. Because we only have like, this key points thing is relatively new, so we haven't tested it extensively across many environments, but I think it definitely can scale to like other objects or like other morphologies of like robot that you're using, etc. for sure.
Right, there's one more question, and then I think after that we should move on because
yeah,
we are behind.
For sure.
Why do you think that observation noise helps?
Why does it help? Well, one reason is that like it is like there is observation noise in reality, right? So when you like actually plot the or like when you download the cube pose tracking data for a stationary cube, there's a certain amount of jitter in that inherently. And actually that is what I use to like define, like we use Gaussian distribution for observation noise, and that's what I use to extract like the standard deviation of the noise that we added. And so like that's one reason. I guess another reason would be like, so it's not too reliant on exactly how the dynamics of the simulator are like running. It doesn't like, it's the policy is not producing huge changes in actions for small changes in observation. So it makes it more smooth. So yeah, I would say those are the two main reasons.
The other one is also that it prevents overfitting to perfect simulation state.
Yeah, for sure. Okay, so yeah, I guess if anyone else has other questions, I'm happy to answer them. I'll be sticking around in the chat. Yeah, so.